right, so continuing on equilibrium. What does this K mean, this equilibrium constant? Well, a shorthand way to look at K, and don't write this when you're asked for a equilibrium expression, but a shorthand way to write this K, KKC or KEQ, is really, remember, it's going to be the concentration of your products over the concentration of your reactants. So if K is much, much bigger than 1, that means that your numerator is much larger, so you have more products. So your equilibrium is said to be product favored, okay? And products predominate at equilibrium, meaning the concentration of my products is much, much greater than the concentration of my reactants. Similarly, if that K, that concentration of products over reactants, is much smaller than 1, then the reaction is said to be reactant favored, meaning I have a higher concentration of reactants at equilibrium than I do products. Let's interpret the magnitude of an equilibrium constant. Actually, you do this, bring this in for tomorrow, and we'll look at it at that point. All right, let's move on to manipulating these equilibrium constants. If we look at the equilibrium expression for these two reactions that are given here, okay, I've got this first reaction and another reaction. If you notice, the second one is just the reverse of the first. For this first, my equilibrium constant is going to be the concentration of nitrogen dioxide squared over the concentration of dinitrogen tetraoxide. Okay, and they plugged in numbers from somewhere. If I reverse it, what happens to that Kc? Well, I have the equation. I can write the equilibrium constant. It's going to be the concentration of the products, which is N2O4, over the concentration of the reactants to the power of the stoichiometry of the coefficient in front of it. So it's NO2 squared. Hopefully you notice that these two reactions, or these two expressions, are just the inverse of each other. So if I were going to invert an equation, and I have its Kc, when I invert this, that's if we call this Kc1, and this is Kc2, Kc2 being the reverse of Kc1 is going to be the inverse of Kc for the first system. Okay, so it's just the reciprocal. What happens if I multiply an equation by a coefficient? If you notice, I multiply this first equation just by 2. Okay, so I'm doubling the whole equation stoichiometrically. What happens to my equilibrium constant? Hopefully you notice that, again, I'm going to call this Kc1. Oh, I have to put it in pen mode. So I'm going to call this Kc1, and I'm going to call this Kc2. If you notice, Kc2 is really just Kc1 squared. And that is the number that I multiplied Kc1 by to get Kc2. That's supposed to be an arrow. Okay. So the equilibrium constant of a reaction that has been multiplied by a number is the equilibrium constant raised to a power that is equal to that number. Now the equilibrium constant for a net reaction made up of 2 or more steps is the product of the equilibrium constant for the individual steps. I've lost all of it. So this, I'm looking for KC2, call this KC1. KC2 is the reciprocal of KC1, so that will be 1 times 10 to the 30th if you take the reciprocal of that. This K for the original equation is very small, 10 to the negative 30. So this means if K is very small, okay, much less than 1, that means that it is reactant, or the reactant predominates. Here, the equilibrium is very, very large, so here the products dominate. And it makes sense if I flip an equation. If the original one was reactant dominant, and I flip it, it makes sense that the reverse reaction would then be predominate in the products. Okay. If you would pause the screencast and attempt this on your own. You should get that the answer is 0. Oops. The answer for the Kc for the reaction should get 0.12. Are there any units for the equilibrium constant? No, there are no units. Okay, unitless. Okay, let's talk about a case where my reaction mixture has two different phases in it. Okay, it's a heterogeneous equilibrium, so everything is not in aqueous, everything is not in the gas phase. And where we run into trouble is when I'm talking about solids or liquids that are in a reaction. Those solids or liquids are essentially constant, the concentration of those. We don't talk about the concentration of water. We don't talk about the concentration of, say, aluminum, if I'm using aluminum in a reaction, right? You can get a concentration by multiplying the density by its molar mass. That gives you a concentration, but it doesn't change throughout the reaction because it's a solid or a liquid, so I'm not changing that concentration. So when we use, or when we have a solid or a liquid in equilibrium, the concentration of those solids or those liquids, because they are not changing, they do not appear in the equilibrium expression. So in this, I have a solid, lead 2 chloride, in equilibrium with the lead ion and the chloride ion. The equilibrium constant would only be for the products, the two components that are in solution. And remember that that coefficient becomes the power for that. Now, that doesn't mean that I don't need some of those components for the reaction to actually occur. It just means that the position of the equilibrium is not dependent on it. So in this equilibrium, calcium carbonate solid being in equilibrium with CO2 gas and the calcium oxide solid, the Kc, the equilibrium constant based on concentrations, can you guess what it is? Kc would be just the concentration of the CO2. Now, in the special case where I have gases, I can use something called a Kp, and this is where I can write the equilibrium constant using partial pressures of the gases that are involved in that reaction. So in this case, the Kp would just be the partial pressure of CO2. Okay, so pause this and see if you can write these two. So for this first one, A, remember my Kc is going to be based on concentration, and it's going to be my products. This is a liquid, so it doesn't enter into my equilibrium equation, over the reactants, so it would be the concentration of CO2 times the concentration of hydrogen. For B, be the concentration of products, but tin doesn't enter into it because that is a solid. So it would have CO2 squared over the reactants. Again, solid doesn't enter into the equation. I'm going to have to do something about my pen. And that should be a 2 as well. Okay. Okay, see if you can write the equilibrium expressions, equilibrium constant expression for these two. Pause it if you need to. And we will look at these in class.